before going on to explain the existence of these discrete energy levels, I would like to make it so that I'm not just making a pure claim, but I want to speak to what the experimental evidence is for the discrete levels. This discussion also will get us thinking and give us some more evidence with which we can compare our theory. So that this will be actually very much worth our while. So the experimental evidence for this, one of the greatest experimental evidence, or the most convincing, actually comes from the atomic spectra. So in an atomic spectra experiment, what you do is you take a gas of the atoms that interest you, in this case it's hydrogen, and you put them in a chamber. And so you're going to have a bunch of atoms in your gas here in my chamber. So this is a gas that we're going to put in here. And then, of course, in our case, the atom that interests us is hydrogen, so we'll put all hydrogen atoms. And then what you do is you stimulate this gas somehow. You know, who knows? You might put in a very high voltage with some electrodes and put some electrical discharges through here, something to get these atoms all excited and out of their lowest energy configuration. And when you do that, what you find actually is that radiation begins to come out and they emit light at different wavelengths lambda. Now, that's the setup. Now the results are just as intriguing. So the results that you find when you do this, if you measure, for example, the brightness that you observe at different wavelengths, for different wavelengths lambda, what you find is certain preferred discrete wavelengths. These wavelengths make up a beautiful spectrum, and you find these very sharply defined spectral lines. And it's actually very beautiful when you look at them. The longest wavelength line comes in around 656 nanometers. It's a nice deep red, rouge type color. And you find a very sharp peak at that one particular wavelength. And that's known as the H alpha line. Alpha meaning the first one, and H for hydrogen. But there are other lines that one sees. You go up, you find other colors in the rainbow at, going more into the blues and the greens. I forget all the exact values that you see. What you do observe, though, is that these lines begin to scrunch together, and they start to go up. I forget how many you can actually see visually. They begin to get to shorter and shorter wavelengths, which then corresponds to higher frequencies. We're getting now into the deep violet and ultraviolet, but there's a whole series of these peaks, and they finally reach their own accumulation point just around 365 nanometers. Now, there's a beautiful and mysterious formula that came out of these experiments, and this is due to Balmer. So Balmer discovered a beautiful formula that is able to predict actually all of these wavelengths. And so we're going to use that formula in our analysis. And this formula states that the wavelength that you should expect, these can be labeled by discrete integers n, and these integers actually range, in his case, from 3, 4, 5, mysteriously starting at 3. And he found these wavelengths are fit perfectly by the following formula. You have this accumulation value coming back in, 365 nanometers. And then that integer n comes in a very interesting formula, n squared over n squared minus 4. Now, these lines are not directly the energy values in the hydrogen atom. We have to do some analysis and to make some connection between these and the actual energy values. So here is how our analysis will go. So the basic assumption underlying the analysis is that by conservation of energy, we know that this light is actually coming out in our discrete energy packets as photons with energy E equals h nu. And if an atom is going to emit a photon of a given energy, by conservation of energy, the energy within that atom must be changing. So what we're really seeing here are changes in the energy in the atom. So what we're saying is there's a change in energy, delta E, for the atom, for each of these atoms, and it's coming in the form of h times some frequency. Now the frequencies we can relate directly to the wavelengths. We know that nu is h over lambda. So this, nu is c over lambda. Nu equals c over lambda. So my product then becomes h times c divided by lambda. And now this is something I can work with. You will recall there's a nice value for h times c. I had given it to you before as 12,000 in units of angstroms, but here we're dealing with nanometers, which are 10 times bigger than the angstrom. So the number is correspondingly 10 times smaller. Instead of about 1200, instead of about 12,000, it's about 1200. And I believe the actual value is more near 1240. And h times c has units of distance times energy, so this is in units of nanometers times electron volts. And now we can divide by these discrete values for lambda, which then I can simply copy the formula, 365 nanometers. And I want to get all the math out of the way. So let's also pull out this factor of 4, so I can divide by 4. And then I can write the remaining factors, which are n squared, and I've pulled the 4 out of the denominator. So the denominator now is simply n squared over 4 minus 1. Now, we can evaluate all of the numerical factors. Right, I have nanometers over nanometers, so that's great. I'm going to get an answer in electron volts. 1200, this is a little more than 1200. This is a little more than 360, so it's about 1200 over 360. Both of those we can divide by 12. So 1200 divided by 12 is 100. 360 divided by 12 is 30. So we have 100 over 30 is about 3.3. Next, we have the factor of 4, which is on the bottom of the bottom. So it comes up on top. So I have to do 4 times 3.3, which gives me 3 times 4 is 12. For the 0.3, that's another 1.2. So it'd be about 13.2. If you put in the actual numbers, it comes out beautifully to our 13.65 electron volts if you put in all the very official numbers. What's left then is to flip over this ratio of these interesting factors. So if I write this up into the numerator and flip it over, I have n squared over 4 over n squared, which gives me 1 over 4, and then minus 1 over n squared. Now here's where things get interesting, right? What we're saying is that we only observe certain changes in energy in the atom, right? And these changes in energy also come with certain very discrete values. Right? We're never seeing a change in energy that is something like, something in between these values. We never see something like that. So it really feels like we have something where there are only certain allowed energies, and then this would explain why there are only certain allowed energy differences. You never have sort of an in-between situation in the energy of the atom, and that's why we never see an in-between situation in the energies that come out as the photons, in these energy differences, in other words. So it feels like this really should be an energy difference between two different energies. And you can see it really is coming in the form of a difference. It really looks like it's something like minus 13.65 electron volts divided by n squared. That would take care of this term, minus another term. Now that term is the 1/4 term, which comes in with a plus sign. So I have to put in a double minus sign here of minus 13.65 electron volts. And what's even more intriguing is that this 4 that goes on the bottom is actually 2 squared. So it looks as though this fits the same pattern of energies as this term here as well. So this gives very strong evidence that there are these certain allowed energies in my hydrogen atom that take the value minus 13.65 electron volts divided by n squared. And if we were to make a diagram out of this situation, what we're saying then is I plot the energy, say, on the vertical axis, and then this line here would be 0 energy. It seems that I've got a series of energies here where this n can be 3, 4, 5, etc. And this energy level has the factor of 2 in there. So it looks like the lowest value I have, the most negative value, will be this minus 13.65 electron volts divided by 4. Then there'll be a smaller one when I put in 3 for n. That would be divided by 9, which is about going to be 9 is about half of 4, so it's probably somewhere around here, about minus 13.65 EV divided by 9, and then you can do it divided by 16 and 25, and you have a whole series here. And what we seem to be seeing is that these observed energy differences that correspond to my photon energies come out occur because I go from one of these levels, right, down to this lower energy level. The energy of my atom goes lower. That means it's releasing energy, and then what it looks like is happening is out of this comes h nu, a photon, with an energy equal to the change in the observed energy. And the energies seem to be coming between 3, this level, which gave me the 9, n equals 3, that's what this one is, and n equals 2. Or between this next one a little bit higher, which would be between an energy shift from going from this level, n equals 4, down to the n equals 2 level. So in fact, this entire collection of levels, all making transitions down to this 1365 over 2 squared, explains the entire Balmer series in one very simple explanation. So that would be consistent with all of that experimental data. So that is very exciting. Now, this does beg, though, right? Or it doesn't really beg, but it really raises an interesting question, which is that, well, this sequence that gives me all these energies that give me a perfect explanation of the Balmer series, the allowed energies for my atom have this beautiful formula that can have n equals 2 or 3 or 4 or 5. But what about n equals 1, right? Shouldn't there be much further down here, when I stick in n equals 1, that would give me an actual 13.65. It's a little hard for me to draw. I don't want to use up too much screen space here. But minus 13.65 EV would, of course, correspond to my n equals 1 energy, if there were such an energy. But you'll notice, right, this value is just at 1/4 the size of this value. So there potentially could be transitions from all of these different levels now down to this n equals 1 level. But you will notice that these are all much larger energy differences. And they're so high, this would actually be transitions, if these made photons. Their frequencies are so high, this would be in the far ultraviolet, the far UV. But it turns out actually these were eventually discovered and observed. And there's a whole additional series called the Lyman series of lines in the far UV. And sure enough, their frequencies, h nu, correspond precisely to our formula, where you go from En, where now n can be one of these levels. It could be the second level. That actually is where the Balmer series ends up. You could start from there and make a transition down, or any of these other ones. So n could be 2 or 3 or 4 in the Lyman series, minus then E1. So we have direct evidence also for the existence of this lower energy level, and this then as the ground state of our atom. So that then provides the evidence that we really have this sequence of different energies, and that we are observing atoms with those energies when we make these measurements in a spectroscopic context. But that then corresponds to this sequence of energies that get closer and closer to 0, and their spacing gets decreased. All these energies then, we've just learned, are following this nice formula. Again, just to repeat, 1365 EV divided by n squared. And that's the evidence we have for that spectra. Now, This is really quite mysterious, as we've said. So what we want to try to do now is to build a theory that can explain this. As we've said, the Heisenberg analysis would just kind of give us a smeared out distribution. It has no idea of discrete allowed energies or energies that you just never see. So we need to go to something more fundamental than the Heisenberg principle. Fortunately, we have something available to us. You will recall we derived the Heisenberg principle from the de Broglie hypothesis. So the idea is to go back to our more fundamental de Broglie hypothesis and to see if we can use what we know from that hypothesis to build up a new form of analysis that then would be fully capable of explaining precisely these energy values.